I prefer to speak without the mic. Is that okay back there in the back? You can hear me okay? My name is Jordan McBain. I'm a software engineer at Broza North America. This is a talk on a design pattern for the higher end of the spectrum of network communications, basically addressing the problem that arises when shared variables are used badly in large-scale architecture. Broza is a Tier 1 supplier of automotive components to the automotive sector. We provide window lift functionality. We were the first provider of power-operated tailgate and various drivetrain solutions and cooling solutions. So, shared variables are a great tool, and in NI's suite of solutions to help you get started, there's a wide range of options available: shared variables, network streams, and depending on what your use case is, one is possibly more suitable than another. What tends to happen in the large-scale scenario, and NI, I think, states this fairly explicitly, that shared variables aren't really the best solution for a very large-scale application. So while they're a powerful tool, they tend to result in poor code, again, in the large scale. So I did my PhD in condition monitoring of a gearbox subject to varying operating conditions, so I'm a condition monitoring guy. And I've had the ambition on my own time of building a complete condition monitoring system. And one of the problems in that class of problem is communication architecture used for computers to interact with one another. So in my case, Mimosa CPA standard is the network communication protocol. But there are other protocols that are of interest, I think, to people working in this domain, like Cobra. So it's useful for a software architect to be able to build his or her own solution so that other more interesting problems can be integrated into the solution. So this is an object-oriented design pattern, and really it's based on the reactor pattern, which is in fact part of the shared variable engine under the hood. I'll give you my supposition on that later. So the idea is to have a communication tool that all of your processes block on only on one communication tool. When things aren't properly architected, even in my own experience, I find that when I'm trying to determine the state of a state machine, which is basically my view of a process, I'm checking multiple shared variables, checking multiple FIFOs, just to determine what state I should move into. So to get rid of all of that, we move to an architecture where we pull on only one communication pattern. So the goal is to provide an online subscription to variables and possibly to do so dynamically at runtime, which is, again, possible in the shared variable engine, but the means of achieving it is slightly different. So you see here NI's view of their communication protocols that they have available, and again, the slide just stresses the distinction of the use cases for each of these design patterns. The shared variable engine, I think, is probably the most powerful one, and maybe easier to use. But again, that depends on your point of view and your use case. So I presented a much earlier version of this at the Southeast Michigan User Group meeting in December. It was a very rough sketch at that point, and there were a number of deficiencies. I had strings that were used to identify shared variables, which is still somewhat the case, but it's just an initialization use for strings. The pattern was static. You couldn't dynamically create and destroy variables at runtime throughout the life of the program. And it wasn't really ready for large-scale application. No consideration was given to streaming. And today's presentation code that I will show addresses most of these issues. So, just a very quick introduction to object-oriented design. In LabVIEW, it's basically like a library that has a set of VIs that can access a cluster that's contained in the library, and only those VIs which are members of that library can access that cluster. That's the starting of it. So to define a class, as you cluster associates to the class data, and this is sort of a UML diagram here, and the VIs correspond to the access routines, which are able to access the elements of the class. So in software engineering, it's a software module. A class can be a software module, which is a rigid interface specification that enables encapsulation and information hiding, and ultimately reuse. Inheritance and polymorphism. So if we have that concept of a class from the previous slide, and we want to extend what's capable of doing, we can define a new class that inherits from class A, and I skipped the letter for some reason. And it takes on all of the data of the previous class, and then adds or extends new data. And obviously the functions, the access routines are also augmented. And then again, you can proceed in the same manner and carry on just as had been done before. Normally, there's some sort of mean of multiple inheritance, and you can not only inherit you can inherit multiple classes in a new class, but in LabVIEW, this isn't really possible right now, unless I missed something in Keynote. I only came today. So, in a multi-threaded environment, that you will have various processes running, each with its own objectives, logging, error handling, a channel manager, another process, the user interface, all just on one PC. And you need to communicate data from one process to another. And obviously we typically use queues for this sort of application. So some processes will be interested in subscribing to various data of other processes, and they'll also be interested in publishing data from their own process. So each process has its own interests, and also provides a means of satisfying another process's interests. So what I did, I introduced another thread called the broadcaster, the published variable broadcaster, which runs and handles all the networking and multi-threaded intercommunications. So this could be deployed on a compact Rio. Over the network, it would announce itself, and other elements on the network would respond to that announcement, a multicast UDP announcement, and they would all coordinate themselves communicating together. Now, the shared variable engine, I think, has some sort of more hierarchical architecture, though I don't know all the design factors that were in it, that went into it. But the goal of this is to completely decentralize the communication protocol. So there's no servers. By virtue of the multicasting message, each network element announcing itself on the network and registering with each other to exchange information. One avoids the server architecture. So they're all peers. So the reactor pattern has 4 forces in it. This is the standard reactor pattern. The one I'm trying to propose today is a dynamic reactor pattern. The application should only block on a single source of events, which is what the goal is in this application. So each thread only blocks on one queue or FIFO, and it cuts down on pooling. It avoids context switching and synchronization issues. It should enable adding new services and published variables. And it should shield code from complexity of multi-threading, synchronization, and network communications. So if you're interested in this sort of design pattern, this is a great book. It's written primarily for C++, but most of the diagrams are just UML. So if you like object-oriented design, this is a good book to read. I suggest skipping the overview chapter and going right into the patterns, because the patterns are easier to read. Oh, incidentally, you will, if you've ever had an application running and you have a user interface on a PC and one on the RT, if the two disconnect from one another, you'll sometimes see a chain of error messages that show up on the screen, because the shared variables are trying, and utilization on the RT will go up to 100%, at least up to 2013. I haven't used LabVIEW 2014 or 2015. So those error messages, if you search them, they're part of the adaptive communication environment, ACE, which is C++ network architecture, which this book is based on. So my supposition on that is that NI has used the ACE environment under the hood. So the reactor pattern that we're proposing today synchronously waits on events from multiple sources, integrates multiplexing and dispatching events to processing services, decouples dispatching and multiplexing from the application-specific processing. And I'll show you my code, the internals of it. The example I have, the actual application is fairly trivial, but I'll take you into the code for the networking architecture, and you'll see how I reused the design patterns in the simplified example to gain more powerful functionality. So part of the limitations of the existing reactor pattern is that the class allows registration and removal of event handlers. The reactor waits on a group of operating system mechanisms. When OS mechanisms trigger the reactor looks up the event handlers registered for that event. It calls the handlers back by a pointer. So in LabVIEW, that would be a data value reference, which potentially causes blocking, or deadlock rather, at the operating system level. So one of the goals of this pattern is to remove the possibility for blocking, deadlock at the operating system level. And again, you can still have deadlock at the application level with queues, depending on how you use them, but you don't need to worry about the operating system, deadlocks at the operating system level. It's a nice pattern for a single-threaded application, but for parallel applications, there's concerns over race conditions, deadlock, non-preemptive nature, and it's difficult to debug. So comparing two environments, the multi-threaded environment on a single computer, as I've already said, one process is interested in subscribing to other processes' data, and it also is interested in publishing that data. But if you look at a distributed environment, the problem is really the same thing. Distributed processes are interested in registering to other distributed processes data, and they're also interested in publishing those distributed processes. So here, really, I've identified an abstraction which makes the problem basically the same thing. So there's strong reuse potential. So the design pattern is as such, with the broadcaster and various services on one computer. So again, the idea is that each process will only block on one communication mechanism. The service provides a queue to the broadcaster, and the broadcaster says, okay, well, here's my queue. If at any point during the course of your lifetime you want to know about other variables that are presently published, then just tell me and I'll start sending them to you. And then we add the network environment where there's a broadcaster running on other networked levels, networked computers. And the broadcasters basically provide a network abstraction layer. So if you think of every row in here as a compact Rio, and every person at the end of the row as a published variable broadcaster, and each person in the row as a service which publishes variables and is interested in subscribing variables. The coordination is, you shake hands with the person at the published variable broadcaster, you exchange telephone numbers basically, and when you're interested in exchanging data or registering or receiving information about published variables, that all happens with pre-coordinated communication mechanism with comms. And of course, at the network level, the broadcaster basically hides the details of the networking interface. So at this point, I'll go to my demo. It's on a different screen, so the one screen size rule is a little bit highlighted here. But you'll see here that I have a thread of execution here. I have this upper level is the network broadcaster, person at the end of the row, and the other ones are services which publish and services which publish and subscribe to data. So this is an instance where when you initialize this publish this service, it uses communication scheme to the broadcaster to tell it that it's interested in receiving information about a variable called Woo1, an aggregator Jordan1. And the bottom process here is another process running, which is a participant of the which is a service participant, and it's not using queue, it's using user event instead of a queue, but it's essentially identical. I just abstracted the communication mechanism away so that you can use the same user interface with with a different communication mechanism. So as I said, this is somewhat trivial, but at runtime, the three processes below the broadcaster each subscribe and register with the broadcaster. They are all interested in the Boolean variable, this one, this right here. So when I change it, this this process tells its published variable aggregator part that it's setting the value of what its value is. When it sets the value, the thread communicates to the broadcaster, and then the broadcaster sends it to anyone who's interested in receiving that information. So as I said, fairly trivial. One thing you can do, if a during the course of a networked operation, some variables and some compact videos are going to go offline, so you can end the life of a variable at any point in time, and you can re-add it later on. So I've ended the life now, and these two processes up here are no longer getting this information and displaying it on the display. But then when we re-add the variable to the aggregator, and the aggregator tells the broadcaster that the variable is online again, then the broadcaster comes back to us and tells us, okay, you're online again, there are people that are interested in receiving this information, please transmit. And so that's what it does. I'll re-add now, and the latest value is displayed. And my stop button is also a published variable. So all the processes register themselves to it. So as I said, this part of the architecture is fairly trivial. It's just an inter-process communication. And it's really at the network layer where things become more interesting. So the published broadcaster at the end of the row, what's going on there is actually kind of, is much more complicated. And so we'll come back to that shortly. So the participants in the design pattern, there's the published variable, which is a data storage class. Anyone using the design pattern will make a published variable and specify the inheritance associated to it. And they can make add whatever data they want to the class so that it can be published across the network. The application will create new ones to handle individual events. The published variable has to be registered with an aggregator to be used, and the aggregator also has to be registered to the broadcaster. So that exchange of telephone numbers has to happen. And so services can subscribe to receive information feeds and should be able to write to published variables. Then there's the published variable aggregator. And as we said, it stores or aggregates published variables. When a variable is updated, it transmits to the broadcaster for dispersion. Only transmit to the broadcaster with active subscription. So every time that there's a variable updated, if no one's interested in receiving information about that data, then the broadcaster, in fact, the published variable aggregator does not transmit the information over the queue. So you have processes that are interested in publishing and in receiving. And so to handle that, I made another class called the service class, which inherits the aggregator interface and provides a means for registering to receive information. So it can be both an aggregator and a subscriber of published variable information. So the published variable broadcaster, people at the end of each row, passes data between services depending on the registration information provided. It acts as a network and concurrency abstraction layer. And as I mentioned earlier, that my previous example was static. At runtime, you couldn't register and add new variables. So I made a distributed published variable broadcaster, which is basically the same thing as a variable broadcaster. It inherits the interface of it. But what it is it's basically another queue to the broadcaster. And when anyone uses the interface for the distributed published variable broadcaster, they pass in their information as they would with the regular broadcaster, but that information is passed via a queue to the broadcaster within the interface. So the distributed nature of the distributed published variable broadcaster is hidden from the operator. So they essentially think they're interacting with the broadcaster. And so this starts us on a discussion of inversion of control. And I understand that Steve Mercer gave a presentation on inversion of control, but I wasn't able to attend because I only came for today. But hopefully this presentation ties in very well with his. So each of the command objects that I have has an access routine called a receiver, which is friended to the broadcaster. And we'll talk more about that later. Broadcaster, when it receives the object, it calls the receiver of the communication element, and the receiver then calls, you pass the broadcaster into the receiver access routine, and the receiver then calls the correct access routine of the broadcaster, which makes my head spin a bit, but I can show you the code later. Then at the network layer, there's a published variable broadcaster, a multicaster, which is a published variable aggregator. Hidden inside the broadcaster's run routine, sends UDP multicast messages announcing its presence on the network. It has a published variable acting as a queue for newly identified or discovered IPs, which another participant registers to. So inside the broadcaster is the normal multi-threaded environment component that handles concurrent threads, and then the networked interface scheme is here. So this is the multicaster, and it sits there and it sends multicast messages out over the network announcing its presence. Next participant I'll discuss is the network facade, which registers to the multicaster's newly discovered IPs published variable, and once it receives what the new discovered IP is, it starts the communication to begin enabling registration of aggregators and variables between two network elements. So it attempts to set up the communication. If successful, it publishes this as a registered IP to the multicaster, which then ignores any multicast messages received from that IP. The network facade asynchronously launches an aggregator to represent all the aggregators on the distributed computer. So, coming back to my row analogy again, the published variable broadcaster will launch new published variable aggregators that represent published variable aggregators on the other compact reos or computers. And it basically registers itself in the same way that a normal published variable aggregator would register itself with the local broadcaster. And the network facade transmits published variable updates to it, and then that facade of an aggregator, it then transmits internally to the local broadcaster. So the broadcaster launches aggregators which tell the broadcaster what variables are available. Broadcaster then announces those to the other services, the other processes in the environment, and they are able to say, yes, I'm interested in those. Like the published variable broadcaster, to represent that the network aggregators will launch the thread, and the processes on the local computer then will receive updates just as if that network aggregator were were local to the computer. So this is very similar to the active framework. In fact, I think this design pattern would mesh well with the active framework for providing network facilities. So there was a design decision here. I could have, for every networked broadcaster that's available to the local broadcaster, I could have launched a thread and had that thread hold the not only its communication queue, but also the networked TCP connection to see if there's data on both going back and forth. And then for every aggregator, network aggregator that's launched, you would have threads context switching back and forth. And if there were a lot of them, then there would be a lot of context switching. So to avoid that, and only to have a context switch happen, I have all of the polling back and forth happening within the network facade. And I'll show you the code for this. So the COM scheme, the published variable is what we're trying to pass around, but there's a lot of administrative routines that are going on. Published variables announcing new published variable aggregators announcing the availability of new published variables, the destruction of aggregators during their lifetime to the published variable broadcaster. So to enable not only transmission of published variables from one thread to another and one computer to another, we have to be able to have some means of passing administrative information around. And if we retain our goal of attempting to only block on one communication mechanism, then there has to be a more generic form of the published variable, which the COM scheme is responsible for transmitting. So as I showed you in my code, you could launch a process based on queues, or you could launch a process based on user events. And so the COM scheme abstracts those details away. So as I said, user events, queues, and FIFOs, maybe even active framework queues. Then the COM element is the more abstract form of the published variable. I have a UML diagram to demonstrate later on. So the objective, as I said, is to try and block on only one resource. And we generalize that data type by a communication scheme. Child classes, so aggregators need to have some administrative information passed between them, and broadcasters need to be able to receive administrative information. So each child class of the communication element is both, there are two main child classes, the broadcaster configuration settings and the aggregator configuration settings. So this administration, this element permits this administrative registration and deregistration of variables and aggregators throughout their lives. So here is the UML diagram. This is a published variable. It's the main way in which data is transmitted around and would be used in the application there. Ultimately, the most abstract form of it is the communication element. But in between that, there are other communication elements. There's a service communication element, again, for aggregators and services, and there's a broadcaster communication element. And just as the nature of stepping through the problem, I put a published variable as a child class of the broadcaster communication element. So these all share similar interfaces, and they're able to be transmitted by virtue of sharing that same interface. They're able to be transmitted over a communication scheme, which could be a queue, could be a FIFO, user event, active framework communication pattern. And then I mentioned that in order to facilitate communication between the aggregators and broadcasters, there are various other communication elements that set an ID. So rather than just using strings to identify the name of to identify a particular aggregator, broadcaster, or published variable, I use an integer. But in order to use the integer effectively to identify one of those elements, it has to be transmitted between the elements at any point in time. And there are other routines like end, which basically terminates the aggregators and broadcasters. So the published variable aggregator uses a communication scheme through which it communicates to the published state broadcaster and receives updates on published variables and registration information. The distributed published variable broadcaster, as I mentioned, is basically the same thing as a broadcaster. It enables registration and deregistration throughout the life of the design pattern in a distributed fashion, and presents the same interface as the published state broadcaster would present. And then the service is basically a published variable aggregator, but as I mentioned, each element, each process in the distributed environment is interested in receiving published variable information and it's interested in broadcasting it. So to enable it to broadcast information, it's inherited from the published variable aggregator. And it also brings on its own interface elements to enable it to subscribe to published variables. And then at the high level of the design pattern, there's a network facade, which basically hides, which is an abstraction layer for the network interface that allows published variable aggregators on each contact Rio computer to interface with other aggregators on other computers. So during the course of developing this pattern, I stumbled on inversion of control in LabVIEW, and it's nice. It's basically the Hollywood principle. Don't call us, we'll call you. So whereas the thread would normally run on its own and make decisions about what happens next, other threads are able to influence how any other given thread behaves by changing the values of variables to which that other thread is registered. So that involves using a lot of friendship relationships and community scope in LabVIEW. And one of the best part of inversion of control with friends and communication schemes is it avoids bad code. It avoids you testing to see if the received variable is of this class. If it's not of this class, then is it of this class? And if it's not of this class, then perhaps it's of this class, and you can of course cascade that on forever. It's very inefficient. I mean, just the way it's set up, it's inefficient. But this testing is also inefficient. So the inversion of control avoids that. I also use another way of doing inversion of control, which I'll show you when I get into more complicated aspects of the code. So there's strong reuse potential of this pattern. There's reuse between projects that developers have, which is sort of the standard the standard way we consider reuse. But there's also, more importantly, there's an opportunity for reuse within the same project to enable network abstraction. So in my view of monitoring and control solutions in a real-time environment, there are two major software architectural challenges. There's distributed information in a distributed environment, and then there's channel management, channel managers. So streaming data and analyzing that data with routines. In my case, in particular, I'm interested in being able to run data analysis routines and add them to a channel manager at runtime, not just at compile time. So the thought was, well, we'll use a recursive definition of an aggregator. An aggregator could contain other aggregators, and a channel manager could be an aggregator. And in that channel manager, there could be routines, or there could be data processing elements, which are also aggregators, and have various published variables that other elements of the network would be interested in. So I haven't implemented that. It's another step order of magnitude of effort, but I'm thinking ahead in terms of what can be done in terms of reuse. So if the channel manager runs in a single thread of execution, It changes the messaging scheme to array-based scheme, and permits communication between sub-aggregated aggregators. So I'll go into the network aspect of the code just after this slide. But in the future, my intent is to incorporate message priorities, urgency messages, to use a bitmask numeric identifier for variable IDs, published variable aggregators, published variable broadcasters. So the bitmask would have all the information in one, and I think that would simplify addressing access to published variables after they've registered. And so some of this, obviously, I'm just thinking ahead in terms of being able to recursively define aggregators. Integration with Active Framework shouldn't be too hard. And other networking types. So CAN Open and EtherCAT are two network types that are of interest. They basically have streaming data as well as sort of effectively published variables which define how the CAN Open node behaves. You can write to the CAN Open table and change the behavior of the machine. So this pattern, I think, would interact well with CAN Open and EtherCAT, which are both compatible communication standards. And then streaming of data. So the shared variable engine allows you to stream data. NI identifies that the shared variable engine is good for low to medium speed streaming. And so I think this pattern actually is effective in that same manner. It's probably not meant for high-speed data streaming. You would use a proper FIFO or another queue, depending on your application, to stream data. But I think there are improvements that could be made that would better facilitate streaming. So, just getting a reference again. Inside any given computer, there might be a number of threads running, which are aggregators or services which are aggregators and subscribers, and all of that information is registered and communicated over the network broadcaster. The bottom two threads in this code are the network aspects. You could get rid of this, and this would be perfectly fine. Multi-threaded application with no networking interests. I just wanted to show you inversion of control here. So as I mentioned, every process, every thread in this pattern will only block on one communication mechanism. So the network broadcaster only blocks on one communication scheme, whenever we find that to be at runtime, and it gets received. It has a receive routine, which basically reads off the queue or reads off the user event, and then it passes that into a routine, access routine, which is common to all the elements that could be passed to the broadcaster algorithm. So if I double click on this, it brings up a whole bunch of access routines that are generated through inheritance. So you can see here there's terminate. So if I go into terminate, terminate receive, if you send a terminate message in the broadcaster class and you send it to the broadcaster, it will, when you run that access routine, it will then call another access routine in the broadcaster. So again, there's the communication element and then there's the broadcaster. The communication element has the receiver function, access routine, which the broadcaster calls, and then when the receiver routine is called by the broadcaster, the receiver routine calls another routine within the broadcaster. And if your head is spinning, I don't blame you. Every time I've gone to do this, it's been challenging. But basically, what happens is the network element transmitting to the broadcaster is able to change how the broadcaster behaves, and it then invokes various routines to shut the broadcaster down. And just one other example of that. So if I double click here, for instance, a published variable aggregator might want to take a published variable offline, in which case it will send this remove pubvar communication element message to the broadcaster. This remove pubvar class has a broadcaster receiver routine. So if we go into that, and it passes in the broadcaster to itself. And then it calls this communication element, participant calls an element of, or an access routine of the published variable broadcaster. So in this case, we wanted to, the published variable aggregator wants to tell the published variable broadcaster that it's not transmitting that information anymore. And so it basically effectively calls an element in the access routine in the broadcaster to get rid of to tell other participants that that variable is no longer available. So now, then got 10 minutes left, so I'd like to give you a rough overview of the code for the networking aspects. So as I mentioned, there's no server in this communication scheme. It's all peer-to-peer communication, and that's facilitated by a UDP multicast message. So this network broadcaster launches a multicaster process, which basically, where I think this is right, and UDP. So it launches this process which transmits multicast messages and publishes newly discovered IPs to the network facade, which then coordinates communication with other participants in the network. So that's basically all that the multicaster does. It multicasts messages and tells the network facade about newly discovered networked elements. So the network facade is where my trivial example of the Boolean button being pressed stops being trivial, and you can see the real power in the design pattern. So as I said, I had a design choice at the beginning in terms of how network communications would be handled. I could launch an individual thread which would poll each network connection as well as its own published variable, which would result in a lot of context switching between threads, which would be inefficient. Or I could have one thread polling all of the network communications. And so that's the choice I picked in order to minimize context switching. And you can see how it's realized here. So as I'm, again, coming back to the original goals of the design pattern, each element in multi-threaded environment locks only on one thread. So I showed you where that happens in the broadcaster. This is, the network facade is basically it is a service. So it's a variable aggregator as well as a subscriber to information. And all that happens via this routine. So this is the one place where we block in this thread. And so all the administrative details of the network communication protocol are hidden inside that BI. I can bring it up and basically show you what happens. So here's the communication scheme, receive access routine again. We receive the messages, and if it's an administrative message, then we use that inversion of control principle and use this receiver access routine, which is the inversion of control mechanism, to change information inside the network facade about how it's behaving. And if it's just a published variable, then we make that distinction and we tell whatever's listening that an update has occurred and whether or not there's a request to write. And we spit out the published variable that was received. If there was no update received, then the subsequent state machine just continues processing on whatever should occur after that. Now, so that's the service part. We'll go into the network facade part. What's nice about this pattern is this participant handles both aspects of the network communications. It handles receiving and handles sending. So let's go to, so if a published variable was not received, then what happens is we pull all network elements. And that needs some further refinement. I think that it needs to be more balanced in that respect. But basically what it does is it steps through in a for loop of all the network connections. And the protocol, the messaging protocol, basically the first element is enumeration. It tells us what the other network element is trying to send us, whether we should be transmitting a certain variable to it, whether there's a local published variable update that occurred that needs to be broadcast over the network. There's adding and removing aggregators. All of the routines that happen, that can happen locally between broadcasters and published variable aggregators can happen over the network. So all of these routines do achieve that functionality. So if there's a published variable update, as I mentioned, what happens when a network aggregator gets registered locally, a published variable aggregator gets launched. And basically I send a message back to this loop so that I'm not modifying an array that I'm presently operating on. And so registration and deregistration of variables and aggregators. This is not all that tidy. But suffice it to say, it receives the network name of the network participant, and it receives the aggregator's name, combines that so that local aggregators can distinguish between network elements and local elements. And it launches published variables. So there's a generation of a single variable which gets published to the published variable aggregator's interface, which then gets registered with the network broadcaster. So the same thing that happened locally when we start up, network broadcaster starts up, published variable aggregator start up. Each says, here's my communication mechanism. Published variable aggregator says, well, I have these variables. You can tell other aggregators that they're available, or other subscribers that those variables are available. And when they're ready to start receiving it, you can tell me, and I'll start sending them over the queue. That just happens now at the network level. As far as inversion of control is concerned, I really had to think every time I went to do it, and I had to sit and troubleshoot. I thought during the course of this, I came across a number of constraints in how published variables, subscribers would receive published variables, right? So if you tell the broadcaster that you're interested in the error state, the current global error state of the system, and the broadcaster tells you what the current error state is, you need to figure out which access routines to run, or what case to run. So the inversion of control, non-object oriented approach I used was to pass, whenever we pass a published variable out through the communication scheme, we originally, when the published variable tells the broadcaster that it's interested in receiving error information, the published variable aggregator also tells it an enumeration that published variable aggregator will run once the broadcaster transmits that information. So you see here, I have a case structure that's based on enumerations, and that's, in this case, it's network, but I use it in a number of places to simplify the inversion of control with published variable aggregators. I don't have it handy. But basically, when we tell the published variable broadcaster that we're interested in receiving it, whenever the broadcaster tells us, it tells us which access routine we want it to run at the time that we receive that information. And then we don't have to go searching through arrays to find the correct access routine. So that is time, basically, 1:45 right now. If there are any questions, I'm happy to answer them. I do plan on publishing the code for this, as well as a document that describes it in the NI forums. So you see other design patterns in the NI forums. Probably will take me a month or two before I'm ready to do it. I've basically been doing this on my own time, and I don't have the benefit of code reviews with other peers and I'm testing architecture. So when it is published, it's not going to be perfect, but you'll be able to see what I did and the reasons I did it. Thank you for your time.